Alright, I'm Tommy.
I'm Grant.
And I'm Alec, and we're doing our presentation on the Mississippi River. The history of the Mississippi River. The river was formed by glaciers about 10,000 years ago. Native Americans have lived and relied on the Mississippi River since at least 4000 BC. Minneapolis and St. Paul is the biggest community on the Mississippi population-wise, and there are no highways or railroads that run under the Mississippi River. The river was first discovered by Spanish explorer Hernando de Soto. Why we chose the Mississippi River? We chose the Mississippi River because it was the foundation for building the central Minnesota area. It is also the second largest river in the U.S. and the second longest river in the world.
The first longest river is actually the Missouri River.
And the Mississippi River helped Sauk Rapids to become a huge city before the tornado took it down in the 1800s, I believe.
The history of rate of change. Creation of modern differentiation and derivatives are credited to Isaac Newton and Gottfried Leibniz. Derivatives or the rate of change has many different notations, and we'll put 4 examples of them.
We tend to use Leibniz and Lagrange.
So to start off, rate of change, we had to think of what's changing as we go down the river. So we thought, so in order for the river to flow, it obviously can't be going up, it can't be increasing in elevation, it has to be going down. So we chose elevation and width, so we figured that width would also be increasing. So we found that the elevation at Itasca was 1,475 feet above sea level, and it decreased all the way to, of course, 0 feet above sea level at the Gulf. And the width increased from 25 feet at the headwaters to about 2,300 feet around the mouth. And then with these points, we created a linear regression equation for the elevation, as you can see, and a linear regression equation for the width also. So here are the two equations plotted. And by looking at the chart display, you can find the average rate of change of the width and of the elevation from the source of the Mississippi River at Lake Itasca in Minnesota to the mouth of the river, the Gulf of Mexico and Louisiana, by using the equation of the slope y2 minus y1 over x2 minus x1. So using these points, we gathered, and using the slope formula, we gathered the rate of change from Itasca to Sauk Rapids to Minneapolis, etc. We found that, and then we found that from Itasca to the Gulf of Mexico was about 1.90 feet per mile. So every mile, the river was expanding by about 1.90 feet. We used that using the slope formula. And again, we did it for the width. Since the elevation was changing and decreasing, we used the slope formula again and got that the average rate of change from Itasca to the Gulf of Mexico was actually negative 1.235 feet per mile. So about every mile, the elevation was decreasing by about 1.25.
The history of the trapezoidal rule. The trapezoidal rule was used in Babylon before 50 BC in order to discover the velocity of Jupiter along the ecliptic. The ecliptic is a path at which the planets orbit around the sun. The trapezoidal rule is derived from the Newton-Cotes formula, as it uses 2 points. The Newton-Cotes formula is named after Isaac Newton and Roger Cotes, and the trapezoidal rule dates back further than the definition of an integral.
So for anyone who doesn't know, the ecliptic is not a perfect circle like one might expect of planets going around the sun, but rather it's more of a ovular shape. And all of the planets, except for Pluto, which is not a planet, go around the exact same horizontal axis. Yep. Except for Pluto, because that's just doing whatever it wants, like this, compared to all the other planets.
So we decided to go deeper and show them that we decided to find the volumes of the river actually. So we took these intervals, Itasca and St. Cloud, Minneapolis, just like we did with the elevation and width. And we used the trapezoidal rule right here. So we did B minus A to B, which was Itasca to St. Cloud, for example. And then we found the distance from those points. So from Itasca to St. Cloud, it was about 147.07 miles. And then we took the width at Itasca and the width at St. Cloud, added those and then divided those in half and multiplied them by the distance from the previous point to find the surface area in that interval. So we found the surface area from Itasca to St. Cloud was approximately 203,839,020 feet squared. And then to find the approximate volume in that interval, we multiplied by the average depth. And from Itasca to St. Cloud, it was 3.995 feet. So we found that number right there, feet cubed, was the approximate volume for that interval from Itasca to St. Cloud.
However, this is an overestimate because at all points in the river, they are not the same depth. We went off of using the deepest part of that part of the river.
So we went on and we used the trapezoidal rule to find the approximate surface area for Itasca, Minnesota. From Itasca to Minnesota to New Orleans, Louisiana is about 7,647,893,220 feet squared. And when we multiply the surface area by the average depth of 16.373 feet, we can get an approximate volume of 125,216,869,900 feet cubed. This is an approximation due to the fact that the river's always changing with rainwater or flow can also change the depth and the width of the river. So, and when we were doing the distance from each point, we couldn't actually find the distance by the river, but we used by the crow flies.
So optimization. Optimization is a mathematical technique for finding a maximum or minimum value of a function of several variables subject to a set of constraints as linear programming or system analysis. Optimization in rivers is finding the angle for which crossing a river and traveling a certain distance will take the least amount of time. Linear programming arose as a mathematical model developed during World War II to plan expenditures and returns in order to reduce costs to the Army and increase losses to the enemy. So history is optimization. In 100 BC, Huron proved that light travels through the fastest path between 2 points. So in physics, we did a lab where we had a rectangular piece of glass, and we would point a laser in it, and we found that the glass actually changes where the light exits, so it is not a straight line, that it goes through a different path through the rectangular glass. And in 1615, Johannes Kepler calculated the optimal dimensions of a wine barrel. So he took the function of the wine barrel and how it's round and found that function, and he found the area in between those curves. So we used optimization to find the fastest route to walk from and swim from Burger King to the St. Cloud Hospital. There's got to be a relationship there. So there's 4,000 feet north and south, and 750 feet east and west. And we found that the average person will jog at about 7 feet per second, while they will swim at about 3 feet per second. So we wanted to find this point at which they can go from the St. Cloud, or Burger King, to the St. Cloud Hospital. So to do this, we found the point at which we do that. And so we have the function which is the distance going from Burger King to this x, divided by the speed, which is 3 feet per second of swimming. And then we added that to the time at which it would take to walk, which is 4,000 feet, minus this x value, so that's right there, divided by 7, which is your speed. So to find the best case scenario for getting there the fastest, we took the derivative, which is x over 3 times the square root of x squared plus 5,600, 2,500 minus 1/7, and then we set that to equal to 0. So we found that x equals 355.75 feet. That is feet from this point straight down over. And we found that time, which would be 709.30 seconds, or 13.288 minutes.
The calculus supply. Optimization. We use to make the best products with the least amount of resources. For example, is trying to live the longest life with a certain number of heartbeats. Rate of change. Used to find how quickly objects change. Rate of change can be used to find how quickly a baby grows in weight as well as height. Integration. Used to find displacement. Very common in engineering. Can be used to find the volume of an object with curved sides such as a wine barrel.
That's it.